The op-amp integrator is nothing but a better version of the classic low-pass filter when we want it to work as a low-pass amplifier or a low-pass filter, because it also amplifies the signal at the output. Well, pay attention now very closely. This point, I'll call it node X, and because the gain is not infinite, it's of a finite value, we cannot say that this is a virtual ground. We can do the following. Let's use the equation for all op-amps. So whatever we have, this equation holds always true for the op-amp. How much is V plus? 0. How much is V minus? Well, this is Vx. So Vx is... Alright, this is very important because the gain is not infinite, the Vx is not 0. You see, if this was infinitely large, this would reduce to being 0. Now, I will say that a current flows inside these nodes and a current flows outside this node. I take nothing but a KCL here, so the current flowing inside is equal to the current flowing outside, which is the voltage difference over the impedance or the resistance. How much is the impedance of the capacitor? It's 1 over CFS, and with S being the frequency, or better, the speed of the incoming signal. Now, if we take Vx, replace it inside here, and we take 1 over CFS and replace it over here, we get the outputs over the inputs. If you do the math, I will give it to you as an exercise, you can do it yourself. We have the following result. Now we can clearly see that we have one pole in the system, alright? How much is the pole? I simply divide everything with this factor over here, so the numerator and the denominator. This will reduce to 1, and this will be the pole. So if we do the math, SP is going to be equal to so this is the pole. This pole just tells me that when the frequency reaches this point and onwards, alright, in the inputs, this means that the output is going to be starting to reduce and we have the integrating behavior. Let me show you like this. We have some value initially here, I will not show it here, and when we reach this pole, SP, then onwards, the output is going to drop in respect to the input. Alright? Over here, by the way, is the integrating behavior that we expect to see. But previously, we have the low-pass filter behavior. Now, how much is this height? Well, I leave it again to you as an exercise. I will not show it here because it's not very important for what we need to show. Check out the op-amp integrator video I have on this channel later on if you want to see more details. Alright, now for the classic low-pass filter, how much is the voltage here at Vout? Well, this is nothing but a typical voltage divider because the current comes inside here and then goes downwards over here. The current is the same, this terminal is common for Vout and Vin. This is a typical voltage divider from circuit theory. Again, how much is the impedance of the capacitor? And if we do the math, this will be the output over the input, and from here we can find the pole, which will be equal to... Now, let's make some comparisons. Alright, this is a minus here. The sign isn't really important when we talk about the frequencies here. Now, again, we would have a low-pass filter with the frequency being something, and then going downwards. The output over the input, with this being the frequency SP naught. So this again works as a low pass filter, the classic. This height will be less than this height. Because this is an op-amp integrator, because it works as an amplifier, if you do the math, the height will be higher. But this is not the point. The point is why this is a better filter. Let's go and compare these two poles with each other. What if we used the same resistance for both of these two circuits? Then this capacitor, in order to get large enough to simulate the capacitor here, it would need to be multiplied by the gain A or A0, alright, A for this case, plus 1. For this circuit to filter similarly to these circuits, the capacitance here would have to be 1,000 times larger than this capacitance over here. So we see clearly that because of the gain, the capacitor here becomes this gain times higher, stronger than in the case that this wouldn't have been here and we had a typical classic low pass filter. Again, if we try to work similarly and say if CF was equal to CX, we see clearly that for this resistor to be close to this resistor for the same capacitor value, it would have to be 1,000, 10,000 times higher. We would have the same capacitors, and this was, let's say, 1 kilo ohm, alright? Then this resistor would have to be 1 kilo ohm times 1,001, 10,001, 1 mega ohm, 10 mega ohms. This makes these circuits much more expensive, potentially, in order to simulate the behavior of this circuit when it comes to working as a low pass filter. So potentially we get a better low pass filter over here using cheaper resistors and capacitors, but the trade-off, because there is a trade-off, is that for this gain we have to pay with a supply. We have to supply this op-amp with some value, some constant value. So there is a trade-off here. We have to see which of the two is cheaper or more or better for our application, because these things again take some size, right? This has some size, but modern op-amps are quite small, but the capacitors can get quite large. These concepts is key for us to compare with each other the things that we are learning with things that we already know. And that way we deepen our understanding, then we perform better in our exams or academic career. Hope you learned something useful today. Check out the op-amp playlist over here. Study well and take care. Goodbye.